Okay, now let's reiterate what we were just talking about. This section is 37.2. Let's look at what Einstein assumed. Well, he had watched almost 50 years of the Michelson and Morley experiments take place, and again, decade after decade, they proved that the speed of light was a constant to every person. And that verified the Maxwell theory, where c was this constant value. So Einstein began anew and said, let's make some assumptions. I have three postulates. Postulate number one is the laws of physics are the same in all frames that are moving at constant velocities with respect to another. Those are called inertially related frames. It means kind of like if you're moving through space with some one velocity and somebody else is moving through space at another velocity, that the laws of physics in both of these frames are indistinguishable. That furthermore means implicitly that you can't tell which frame you're in. You do not know about absolute motion. You can tell about absolute acceleration, but not absolute motion. So if you're accelerating, you can feel it. So this does not involve near gravity or where things are rotating or where things are accelerating in another way. But if you just have two people floating out in space moving with two velocities, you can't tell the difference. So the laws of physics are identical in inertially related frames, and you cannot distinguish your motion. So that's number one. Number two, the speed of light is a constant to everyone, no matter how the source is done or the observer. That means if you have a light and the light is racing towards you, the light bulb itself is racing towards you, there you are, then it will approach you and you will see the light from this moving at a speed c. If it's moving away from you, you'll see it moving at speed c. If you move toward it at any velocity, you will still see this light at speed c. Or if it's just sitting still, you will see it at speed c. Always, irrespective of the source and the observer motions, you always see the speed of light as the same. The third is often ignored. This third assumption is that the relationship between space and time is linear for the four dimensions. This is a little bit advanced here, but it means that time multiplied by c in order to get it into units of meters, x, y, and z in a new frame is obtained by a linear transformation or matrix transformation of constants from ct in the other frame, x, y, and z, so that one person's clock and position measurements are related to another person's clock and position measurements by a constant set of equations. To give you an idea of what this is like, it means that, for example, that ct prime is equal to a constant a times ct plus a constant b times x plus a constant c times y plus a constant d times z. And likewise for x prime, it's one constant d, I'll use e ct plus f times x plus g times y plus h times z. In other words, these constants, a, b, c, d, e, f, g, h, are just numbers. They do not involve the squares, the cubes, the logs, the cosines, or anything else of the values that are there. Well, Einstein showed that space and time are not each invariant, but transform as a four-dimensional object. This is where we get the idea that space and time is four-dimensional from Einstein's work on special relativity. This four-dimensional space-time is described as an event for one observer, and it's related to the event of another observer. By example of an event, I mean, for example, a firecracker explodes. So that happens at a certain time, a certain x coordinate, y coordinate, z coordinate, and a certain t time coordinate. And events like the firing of a firecracker or an explosion or a flash of light or a star going nova All of these things are events in space and time, which is four-dimensional. It's four-dimensional because it turns out we'll see that space and time mix up with one another, like X and Y do under a rotation. If I have X and Y here, and another observer sets his coordinates as X prime and Y prime, we can see that he sees things in a rotated frame of reference. Well, it's actually a similar type of transformation that relates our space and time. So this four-vector of space and time describes and relates one observer to another observer. What are the consequences of that in this transformation? We'll do that in the next section.